Welcome back. This is the last video in connection with diffraction, and I'm going to discuss the second factor affecting the amount of diffraction, and that would be the wavelength of the waves. So here we are. The heading is the wavelength of the waves and how it affects the degree of diffraction. Now, when you look at the electromagnetic spectrum, just at the visible part of the spectrum, you will see that red light has a longer wavelength than orange light, than yellow light, than green light, than blue light, and the shortest wavelength, the light with the shortest wavelength would be your violet light. So on this slide we're going to compare green light with a wavelength of 532 nanometers. That's 532 times 10 to the minus 9 meters, to the pattern formed by red light, which has a 670 nanometer wavelength. Now maybe these photos, the quality isn't that good, so you might not be able to see it clearly. I'm going to highlight it a little bit. There we have the central green band of light. It's much brighter than the other light bands, and you can see that the brightness decreases as we move towards the left and the right of the central band. So to describe this diffraction pattern is, there would be in the middle, in the center, you have a wide bright green band of light, flanked by, towards the left and the right, alternating dark bands and green bands that fades towards the edge of the pattern. If you look at the red pattern, the bright red band in the middle is wider than the bright green band in the middle of the diffraction pattern for green light. There is a good reason for this. The longer the wavelength, the higher the degree of diffraction. So they are directly proportional. The degree of diffraction is directly proportional to the wavelength of the waves. So to conclude, the longer the wavelength, the higher the degree of bending or diffraction or spreading out of light. On this photo, we can compare the diffraction pattern of white light to red light to green light to blue light. You can see that the central band in every pattern is wide and much brighter than the other bands, and that the width of the bands decrease as the wavelength of the light decreases. The first pattern, that of white light, you can see that after the central band and the first set of nodal bands or dark lines, you get the spectrum of colors with the blue light closest to the central light band and the red further. The reason for that is blue light is diffracted or bent less than red light. On this slide, I just want to look at the intensity graph again of a diffraction pattern. So here we have the pattern on the screen. You would see on the screen it's a central, a wide and a very bright central band, so the relative intensity is high, and these places where the graph hits the x-axis are the spots of destructive interference, so your nodal bands, and you'll see that the intensity of the light graph decreases as you move towards the edges of the pattern. Here is another slide that explains exactly the same thing. You must be able to describe a diffraction pattern as well as to explain the difference between the diffraction patterns. So the degree of diffraction is directly proportional to the wavelength of the light. So red light has a longer wavelength than green light, and that has a longer wavelength than blue light, because blue light has a shorter wavelength than green, and as well as red. This is why the red light's diffraction bands are wider than that of green, and blue diffraction bands are narrowest. Here is a video that you would unfortunately not be able to see, but you can Google it. And this brings us to the end of the chapter on diffraction.